Hello, my name is Jason Tsay. I'm here with my co-author, Braz, along with the rest of the team, Todd Mummert, Martin Hirzel, and Avi Shinnar at IBM Research. And today we are here to talk about our work, AIMMX, which is an artificial intelligence model metadata extractor. It's actually an open source library, and it's actually available at the URL down on the bottom. Now, we all know that AI in particular is a very exciting field that's developing with the advent of computing resources and data sets. But one of the problems with thinking about AI models is that it's just highly variable. There's just lots of factors in play. For example, there are numerous different very popular frameworks. There are different types of models out there with different purposes. There's even splits such as traditional machine learning and deep learning. And then once you go into deep learning, there are things like different network architectures. And then all of this is using different data sets. And really, when you start trying to think about AI models, especially at scale, when you're not really thinking about one or 10 of them, but rather hundreds or thousands of them, this variation makes it very difficult to reason about AI models or even really work with them programmatically. What some places try to do, so some companies, for example, they tend to homogenize the platform or the pipeline. So you use one framework, you use one platform, and then that makes it much easier. But if you don't have that choice or you're trying to look for things out in the wild, it's very difficult. So to kind of illustrate this, imagine if you had these shapes on the left, and not really six of them, but like 600 or 6,000 of them. You can see that it would be, because of their different shapes, different colors, it's really difficult to reason about them. But once you generate metadata, such as on the right, you can immediately see that there are ways to cluster them or to really think about them. So for example, you have similar colors, so red and dark red, or similar shapes, so like pentagons, for example, blue and yellow. Now, once you generate this metadata, you can easily reason about what shapes you have, you can analyze them, you can programmatically interact with them, etc. So that's exactly what AIMMX does. What it does is it generates metadata, but instead of shapes, like on the left, we use AI model repositories, specifically public ones from various places. And then on the right, we generate metadata for specific AI models. So this is in general what our work is. So what AIMMX is, and what we're going to talk about today, is that we're going to give an overview of the AIMMX library, and then we're going to generate AI model metadata from public repositories, and then we're going to evaluate our system based on this metadata. And then once we actually have this metadata, then we're able to show the potential of having this. So we can show through some exploratory analyses and some applications, along with a demo of a catalog tool that we created. So let's go over the AIMMX system. Now, in general, how it works is that we take repositories, AI model repositories, we run it through our extractors, and we have a number of extraction modules, which we'll go into in more detail, and then we generate metadata. So standardized metadata, model metadata. And then once you have this metadata, you can do things with it. For example, you can do large-scale analyses, or you can make tools. So let's talk a bit about software repositories and AI models. So we already know that software repositories like GitHub, for example, are already commonly used for AI development. And of course, this community knows that there's lots of useful software-specific metadata that can be mined from these repositories. But the problem is that AI model-related metadata is often not directly viewable. In fact, it often needs to be inferred because these tools, these software repositories, tend to be made for, well, software rather than AI development. So then we need to infer this model-related metadata, and then we need to put it into some common format which we can analyze. So that's exactly what AIMMX does. We first generated a standardized metadata schema. We actually use JSON schema because we make extensive use of JSON for our metadata format. And then we populate the schema with extracted metadata from GitHub specifically. So we have things that are directly extractable from GitHub, so things like the license and other things like that. But we also have, we also infer AI model specific metadata. And at the time of this paper, our current version, we have 5 AI model specific metadata modules: the name, references, or paper references specifically, data sets that were used, AI framework, and the domain of the model. So first, let's talk about the model name. So often, repository names are often not very descriptive or understandable. So if you look on the right, we have an example of entropy-sgd, and then versus entropy-sgd, biasing gradient descent into wide valley. So clearly one is more descriptive, and it tells you something about what this model does or how to use it. And the way we do that is we use essentially a rules-based approach to clean up names from documentation and guess at what is a more descriptive name. Next, we have a paper reference extraction module. So we know that data scientists, they tend to use papers, especially in academia, to discuss and refer to AI models. So we automatically extract references through the documentation through various rule-based approaches. The important one is that we use archive. So archive is a very popular pre-printing service, and it's particularly popular for AI papers. So we look for archive IDs and extract information that way. Next are datasets. So dataset management in general is a common challenge when it comes to developing AI because datasets are highly intertwined with AI development. So it's very important to know what datasets were used. And then the way we detect them is that we look for either things that look like datasets or we look for common datasets that we know about. So if you look on the right, in this case, this NLP model, this text model, uses a textual dataset that's based off CNN/Daily Mail. Next is AI framework. So the AI framework used tells you a lot about how this model was trained or how you could potentially use it. So we detect this by looking through all of the Python files, essentially, so which includes Jupyter notebooks, which are pretty popular with data scientists. And we essentially look for import statements, so things like Torch or things like that. And then we're able to detect a number of popular AI frameworks, so Caffe, Caffe2, PyTorch, TensorFlow, scikit-learn, etc. Lastly, we have a domain inference module. So often the purpose or the genre of an AI model is unknown or is not explicitly stated. But of course, it's very important to know this in order to know how I would potentially use a model or what this model does. Now, when we say domain, we mean the genre or the type of activity. When we say task, we mean the more specific activity. So as an example on the right, the domain here is NLP, natural language processing. The more specific task then is text clustering, or it could be things like machine translation. And the way we actually do this is that we created our own machine learning model ensemble, and we use this to infer the domain. At a very high level, to go over this quickly, we have multiple models to detect the domain. So, and we pay particular attention to vision and NLP. If we find a vision or NLP model, we then further infer the task. If it's not, then we infer whatever that domain was. So it could be playing games, graphs, etc. The reason we do this is because in our ground truth data set for models, there's an order of magnitude more computer vision and NLP models. And so that's why we do this in order to compensate for that. So once we actually have this metadata, of course, the question is, can we trust this metadata? How accurate is it? And then the way we evaluated our system was that we took a bunch of public AI model repositories, so places from model zoos and AI papers. We extract out the metadata, and then we examine the metadata to see how accurate it is or how correct it is. More specifically, how we did that is we generated the metadata from these data sets. So we use model zoos, which are kind of example repositories. Then we also use a bunch of AI papers. So from Archive, as I mentioned, is very popular pre-printing service for AI papers. And then also state-of-the-art papers from a website called Papers with Code. And then we actually do an evaluation per extraction module. And then we also look over the system as a whole and do a holistic system evaluation. So specifically what that looks like is that we actually did 6 different evaluations with different methodologies, and the details of that are in the paper. But the reason we did that is because the ground truth of what we're looking for per module is actually different. So as an example of that, for the holistic system evaluation, you see here that the test size is 80. The reason for that is because we actually had to do that manually to look at all of the metadata that was generated to see how precise, see how accurate it was, false positive, false negatives, and it took a lot of time. So if you look at this as a whole, something that kind of jumps out at you is that, for example, if you look at AI frameworks, our precision is very high. And then other modules, such as references and datasets, the precision tends to be a bit lower. So it tells you that some of our modules are better than others. But in general, our system is roughly has about 87% precision and about 83% recall. So once you actually have this metadata, what can you do with it? So here it's our opinion that once you have this metadata, you're able to reason about it at scale. So the things you could potentially do is you could do an analysis over across a large set of AI models, or you could create a tool that helps you manage all of these models, and that's what we did. So we did an exploratory reproducibility analysis because we know that reproducibility is kind of a problem within AI papers. So we focus on data reproducibility and method reproducibility, and we proxied that by how many models can we find documentation for the data sets and or paper references, with the idea that paper references proxies method reproducibility. So how did they do this? And we found in general that across our data set of 8,000 models, that 70%, roughly 70% of models will document the data set and or the reference. But once you look into more specific domains, so such as vision or NLP or games, data sets tends to drop, but the paper references tends to go up. And that may be because these are more popular domains academically, but that requires further inspection. We also created an example tool of a catalog that catalogs all of these models, and then my co-author Alan will demonstrate this.
Okay, thank you, Jason. So here's the tool that we produce as part of this work. Is a web application that is what we call AI model catalog. Here we is a way to visualize all the metadata that we extract and parse, and also to filter down and analyze the data. So we have this main page that is a list of all the 7,998 models, and we can drill down by all the filter extracted and inferred metadata. So for example, domains, we can filter down by only medical domain, and then we drill down the models list, and also by framework or by tag that is extracted from GitHub. So it's very interesting to filter, drill down and visualize here. Another feature, since it's all metadata, it's all indexed, so we can do search even by specific fields, or we can do a free text search. So we search for Dean, for example. Jeffrey Dean is a very famous Google author. We can have 71 papers found with this name, or if we go for a full search for his name, we can drill down even more. Oops, I think it's just one F. Anyway, let me click one here. And then we can visualize, for example, this one, and then we can see he's an author of a paper. So it's really easy to go by author, by paper title. So every data that we extract is indexed. The domain that we extracted are here, the framework are here, and here we can visualize by tabs. And we can see the definition is the source code, where it's coming from, the training, we can see the extracted data sets. And we also, from GitHub, we store and show here the README, so you don't have to switch to GitHub to see details about the model. Another feature of our dashboard is the stats page, where we consolidate some charts about the data that we extracted, so we can visualize the source of the data that we got, archives, SOTA, or the models used, the total count. We can visualize by number of data sets extracted, also by domain that we inferred. So we can see that the model also has the unknown here value. So and here is the ones that we can even undefine. So it's pretty good finding domains. We can also visualize things that are interested by language. We can by framework and language. So we can see TensorFlow is the most popular, at least in this data set that we extracted, and PyTorch, and this distribution of the used AI frameworks, as well the language, where Python and Jupyter Notebooks are the dominant one. And we add the more data here to analyze, like license or tag cloud. An interesting thing about the tags is that we have a mix of concepts and frameworks and language. So this is a way to, on unstructured data, that we can also visualize, but we have more extractors to infer this. You can, this URL is open, so you can access the URL in the slide and navigate yourself. It's read-only, it's free, it's open source. So you can see the user guide and about for more information. Back to you, Jason.
Thank you. And again, this AIMMX is available at the URL on the right.